Hello everyone, welcome to Algebraic Graph Theory seminar this week. So today, Venkata Raghu will tell us about random analogues of Erdős-Ko-Rado type results. Raghu, please.
So thanks for calling me. So I'll start with the Erdős-Ko-Rado result first, and before that, I'll mention that this is a joint project with which was part of our PIMS CRG and momentum symmetry, which ended last year. So I'll start off by recalling the Erdős-Ko-Rado theorem. Of course, it's a very popular theorem. So it concerns with k subsets of a given n set. We say two k subsets are intersecting if they intersect non-trivially. So what this theorem considers is a family of k subsets that are pairwise intersecting. One such example would be easy to construct. You pick your favorite element and consider all the k subsets containing the favorite element. Now this is an intersecting family of size n-1, choose k-1. Now such families are referred to as stars, and this is a pictorial illustration of one. Now what the Erdős-Ko-Rado theorem tells us is that if n is bigger than 2k, then the size of any intersecting family is bounded above by the size of a star. And moreover, that the equality is achieved when our intersecting family is a star. Okay, so this is the classical Erdős-Ko-Rado theorem. Now, one can interpret the Erdős-Ko-Rado theorem graph theoretically. So consider the Kneser graph. So the Kneser graph as it is a famous graph. The vertices of it are k sets, and we put an edge between two k sets if they are disjoint. So the Erdős-Ko-Rado theorem is a characterization of maximum independent sets, that is independent sets of the largest possible size in the Kneser graph. So if n is bigger than 2k, the independence number of the Kneser graph is n-1, choose k-1, and every maximum independent set is necessarily a star. So that's a graph theoretical interpretation of the EKR. So now this theorem, there's an even stronger version of this theorem, which was proved by Hilton and Milner. So far what we know is that if we have an intersecting set of the independent set in the Kneser graph of the largest possible size, it is necessarily a star. Now what Hilton and Milner proved that if you have an intersecting set, or if you want to consider it as an independent set in the Kneser graph, if it is large enough, then it has to be contained in a star. So this shows that not only the biggest possible intersecting sets are the canonically occurring ones, even the ones which are large enough must resemble the structure of stars. Now, this phenomenon is called stability, and as one can see, this is slightly stronger than the Erdős-Ko-Rado result. Now, Bollobás, Narayanan, and Raigorodskii introduced a slightly different notion of stability, which led to a random analog of the EKR theorem. So that is what we'll be discussing about today in one or two different settings as well. So let me briefly explain what is the random analog of this EKR theorem. So EKR theorem, as I mentioned earlier, it can be considered as a characterization of maximum independent sets in the Kneser graph. So consider your Kneser graph and take a coin with the probability of getting a head is 50. If you get a head, so pick an edge randomly. If you get a head, remove it, and if you get a tail, keep it. That way we'll get random subgraphs of the Kneser graph. Now, the question that Bollobás, Narayanan, and Raigorodskii asked is for what values of P is the independence number of the Kneser graph the same as the independence number of this spanning subgraph that we obtained by doing this random process. So what they were able to prove that was that there's a threshold probability function PC, which is, function of n, so that if your probability P of, deleting an edge or 1 minus P of retaining it is bigger than your threshold probability function PC, then the probability of your random subgraph having the same independence number as that of the original graph goes to 1. And if your probability P of deletion or of retention is less than that of this threshold probability function PC, then almost surely the independence number will not remain the same. And they also showed that when the probability P is bigger than the threshold probability PC, then even the maximum independent sets in the random subgraph will just be the same as that in the original Kneser graph. So, and this one, the original paper, of course, they had this assumption that the K is little o of cube root of n. And then there were later works by different authors for which, it was extended to different domains, namely when n is up to n is bigger than 2k plus 1. So one way to think of it is, you select 2k sets and, you can do a coin toss to decide if you want to consider them as disjoint or not. So even if you forget that, pairs which are disjoint originally are not disjoint, the Erdős-Ko-Rado theorem still holds. So this is another way of strengthening the original Erdős-Ko-Rado theorem. So is that okay so far? I hope there are no questions. So this was the random version of the classical Erdős-Ko-Rado theorem. Now there are many generalizations of Erdős-Ko-Rado theorem to other classes of objects, where we have some sort of definition of intersection. Now, one such family that we looked at is the class of permutations. So you take two permutations on n letters, and we say they intersect if they agree at some point I. That is, sigma and tau are said to intersect if sigma I is tau. As in the case of the classical Erdős-Ko-Rado theorem, one would want to find the biggest family of pairwise intersecting permutations. Now, one way to construct such a family is pick your favorite element I and favorite element j from your n set and consider all the permutations that map I to j. Now, this is an intersecting set of size n minus 1 factorial. As earlier, we'll refer to this canonically occurring intersecting families as stars. Now, Deza and Frankel showed that if we have an intersecting family of permutations, the size of that is bounded above by the size of a star, which is n minus 1 factorial. And later on, Cameron and who proved that this upper bound is met if and only if your family is a star. So this is known as the Erdős-Ko-Rado theorem for permutations. Now, this result can also be interpreted in a graph theoretic manner. So, for which we define a graph called the derangement graph. So, a derangement in the symmetric group is a fixed point free permutation. For example, an n cycle in Sn is a derangement. It doesn't fix any point. Now, we consider the Cayley graph on the group Sn with connection set as a set of derangements. Now, it's not too difficult to see that an intersecting set of permutations is an independent set in the derangement graph and vice versa. So the Erdős-Ko-Rado theorem for permutations is basically a characterization of maximum independent sets in the derangement graph. So the independence number of the derangement graph is n minus 1 factorial, and every independent set of this size n minus 1 factorial must be a star. That is, a set of all permutations that take a fixed element I to another fixed element j. So, as in the case of the Kneser graph, we can ask a similar question. Well, does this result hold for random subgraphs of the derangement graph? So now I'll explain the setup. So again, you take a coin which gives you head with a probability P. Now go to every edge, toss your coin. If you get a head, keep that edge, and if you get a tail, remove it. And in such sense, we get a model of random subgraphs of the derangement graph. Now, as earlier, we'll ask the same question. For what values of this probability P is the independence number of the random subgraph the same as that of the original derangement graph? Now, similar to what was done for the Kneser graph or in the classical Erdős-Ko-Rado theorem, we were able to find a threshold probability function, a function of n, such that when this probability P is bigger than this threshold probability function, so this K here is an error, there should be no K here. When your threshold probability function P is bigger, when your probability P is bigger than the threshold probability, then the probability of your random subgraph having the same independence number as that of the derangement graph goes to 1 as n goes to infinity. And when P is less than the threshold probability PC, then with high probability, the independence number of the random subgraph is bigger than n-1 factorial. And moreover, in the case when P is bigger than PC, the any maximum impedance set in your random subgraph is also a star. In other words, even if you consider like a sparse random subgraph of the derangement graph, the Erdős-Ko-Rado characterization of maximum independent sets holds. So that was a result that we proved. Now I will briefly sketch the proof. So if we consider any spanning subgraph of the derangement graph, if the independence number of the spanning subgraph must be bigger than that of the derangement graph, there are two possibilities. Either we have an independent set, which is in the spanning subgraph, which is of this form, a star union, a permutation which is not in the star. Such sets, will call them as superstars, or we have some, or we must have some independent set which is the same as the size as of that of a star, but which is not a star. Now we'll call this 4 stars, for the lack of better naming convention. So the independence number of the spanning subgraph G will be bigger than that of the original graph if and only one of these two things happen. And now I'll just define this metric dou A for a set, which sort of in some sense measures the distance of a set from stars. Now we will define 2 random variables that will measure the number of superstars and the number of 4 stars of a certain type. So y will be the number of independent superstars in our random subgraph, and xi will be the number of 4 stars such that this metric dou A is I. So in order to show that in the case when our probability P is bigger than the threshold probability, that the Erdős-Ko-Rado characterization of maximum independent sets holds even in the random subgraph, we have to show that the probability of a 4-star appearing goes to 0, and the probability of a superstar appearing also goes to 0. And we also need to show that when our probability P is less than the threshold probability that we showed in the theorem in the previous slide, then we need, if we show that for surely a superstar will appear, then we know that the size of a superstar is bigger than that of a star, in which case the independence number must be big. So this is our strategy for the proof. Okay. So I'll briefly go over how we do this for the superstars. That is, if our probability P is bigger than PC, we'll show that the probability of a superstar appearing is 0. And in the other case, when the probability P is less than PC, we'll show that superstars will appear almost surely. So now this is a seminar on algebraic graph theory, so I should mention some algebraic graph theory. So as a consequence of Delsart-Hoffman bound, we can show that if we take the derangement graph, if we take a star and its complement, that will form a equitable partition. And using that, we can show that there are exactly the size of number of derangements by n-1 edges in this superstar Sij union pi, where pi is some permutation which is not there in this star Si to j, which is the set of all permutations that take I to j. Now, using this, we know that the probability of this random variable y, which measures the number of superstars being bigger than 0, is less than or equal to expectation value of y. So this is the Chebyshev inequality. Now this expectation value of y is bounded over by n squared, which is the number of stars times n factorial minus n minus 1 factorial, which is the number of permutations outside a given star. Remember, the size of a star is n minus 1 factorial. And the probability of retaining an edge is 1 minus p, and we have m edges in the star. So that's why we get this inequality on the expectation value of y. So using this inequality, we can show that in the case p is bigger than pc, this is a threshold probability, we can show that the probability of a superstar appearing goes to 0 as n goes to infinity. In fact, using this equation, we can actually guess what this PC should be. Although now, we have, in hindsight, we know what this probability PC is. But from this equation, we can sort of guess a probability function such that this happens. So this shows that when P is bigger than the threshold probability, almost certainly no superstar appears. Now, we also have a lower bound for this probability of a superstar appearing. So if a superstar appears, this probability is bigger than, if one superstar, so you take your favorite star and consider the probability of, superstars appearing over that star. Now, using this inequality, we can find a lower bound for the probability of a superstar appearing and show that in the case when P is bigger than PC, we can show that almost certainly we must have a superstar. So to conclude, what we have shown is when we have, if our probability P is bigger than that of the threshold probability that we prescribed, then almost certainly no superstar appears. And if our probability P is less than the threshold probability, almost surely a superstar will appear. So if a superstar appears, that means the independence number goes up and the Erdős-Ko-Rado characterization does not flow. Now the only thing we need to show is, well, when P is bigger than PC, of course we show that superstars don't appear, but other kinds of independent sets could appear. So we'll show that that cannot happen. So to measure the other kinds of independent sets, we recall that we describe this random variable xi, where xi is the number of independent sets in the random subgraph of size n-1 factorial, which are not stars. And we associated this measure dou A, which is which in some sense measures like the intersection of A with all stars. Now given a set of permutations, we'll denote EA to be the number of edges spanned in the derangement graph. And we'll define EI to be, the minimum number of edges spanned by this sets of size n minus factorial with this metric rho A being I. Now, it's an easy computations to see that the expectation value of this random variable xi should be less than equal to this n squared measures the number of stars. And this, we are choosing I elements outside this this given star. So we pick a star and measure, take I elements out of the star, and that will give us a set of this form. Now, it has at least EI edges. So the probability of that set being independent is 1 minus p to the EI. So we know this upper bound on the expectation value. So in some sense, we need to, get some lower bounds on edge density of subsets in the derangement graph, through which we can try to estimate what this expectation value of xi is. So now the problem now boils down to finding lower bounds on edge density of subsets in the derangement graph. So how do we do that? So one edge density bound we have already seen as a consequence of del sat Hoffman bound, which we found like the number of edges as superstar bands. Now, as a consequence of this ratio bound, we know that if you have a star and if you have anything outside a star, there are exactly m neighbors in the star for that permutation outside the star. Now, using this, if you take a set T, which is formed in this way, you take a star and take out, a set of permutations A in it, and then add some permutations from outside the star. Now, the number of edges in this thing will be at least B times M minus A, because everything in this B will have at least M minus a number of neighbors because of the del sat Hoffman bound. So, but notice that this bound is vacuous when the size of A is bigger than M, but when the size of A is less than M, it gives us a non-trivial bound. So using this bound on the edge density, we were able to show that if we take 4 stars which are close enough to stars, that is, which have large intersections with at least one star, then we can show that, such a set cannot span enough edges. So the probability of such a set being independent in the random graph is close to 0. Now, but this strategy will not work if your set T is quite far from any star. That is, if it has very small intersection with any star. So for such sets, to find like a low bound on edge density, what we use is we use the spectral decomposition. So we can find like a easy lower bound for any k-regular graph on edge density. So if you have a connected k-regular graph and take lambda and mu to be the least and the second least eigenvalues of the adjacency matrix, and take V to be the eigenspace corresponding to the eigenvalue k, direct sum the eigenspace corresponding to the eigenvalue lambda. Now, using the spectral decomposition, one can quite easily prove this inequality, where this last one is the distance between the indicator function of your set S and it's projected onto this sum of eigenspaces V. And this one, I'm not going to go over the proof of this, but it follows quite easily using the spectral decomposition of the adjacency matrix. Now, in the case of the derangement graph, or in the case of symmetric groups, there's this result by Ellis, Friedrich, and Filmus using analysis of Boolean functions, which shows that if this particular quantity, the distance between the indicator function of a set and its projection onto V, if that particular distance is small, then you have to be that set is close to being a star. That is, the symmetric difference. That there is a star such that the symmetric difference between the set A and a star is quite a small set. So how does this help us? Is that it sort of so if we have very few edges, then the right hand side of the above inequality will be small. So what it tells us is that if we have a set which is far from being a star, that is, it has quite small intersections with any stars, then such sets must have high edge density. So so the probability of such 4 stars appearing is also near 0 because of these two results. So that was the strategy we used. So we first took the superstars and showed that when our probability P is bigger than the threshold probability, the probability of a superstar appearing is near 0. And then we took these things called 4 stars, and the 4 stars which are close in structure with a star, using one sort of edge density measure, we showed that they don't appear. And for the 4 stars which are far away from in structure from being stars, we show that using this particular kind of edge density bound, we were able to show that such stars also do not appear. So now that this kind of random analog has been done for the classical EKR theorem and also for Erdős-Ko-Rado theorem on permutations, we figured, well, let's try to look at other domains where such a theorem holds and see if a random analog of such a theorem can be proved. So what we considered was the domain of perfect matchings. So I'll just recall the definition for matching. So matching on a graph is just a collection of edges in which there are no common vertices. And a perfect matching is a matching that covers every single vertex. Now, we considered the set of our perfect matchings on the complete graph on 2n vertices. And, 2 matchings are said to intersect if, they share an edge. Now, in this scenario, a star will be the set of our perfect matchings that contain our favorite edge E. Now, this is an intersecting family. And the Erdős-Ko-Rado problem for perfect matchings is to characterize the largest families of pairwise intersecting perfect matchings. And this has been done. And it's exactly similar to the classical Erdős-Ko-Rado theorem. The size of any family of pairwise intersecting matchings is bounded about by the size of a star. And the equality is, and we get an equality if and only if an intersecting family is also a star. Now, what we were trying to see is if a random analog of such a result holds. Now, in order to, prove a random analog, we first need to shift it into a graph theoretic setting. Of course, there's a graph theoretic setting here as well. So we consider the derangement graph on perfect matchings. That is, a graph in which, vertices are perfect matchings, and we put an edge between 2 perfect matchings if they're disjoint. Now, the EKR theorem for perfect matchings is basically a characterization of maximum independent sets in the derangement graph. So once again, what we can say is we can we can define a model for random subgraphs. So you consider spanning subgraphs in which each edge is included with probability P independent of each other. Now, in this scenario, we were able to prove an analogous result in a sense that we found a threshold probability PC, so that when the probability P of deleting an edge is bigger than PC, then the probability of a random subgraph having the same independence number as that of the original perfect matching graph goes to 1 as n goes to infinity. And when your P is bigger than the threshold probability PC that we defined above, then almost surely this Erdős-Ko-Rado characterization of maximum independent sets in the derangement graph does not hold for the random subgraph. And further, we also found that when this probability P is bigger than this threshold probability, then not only the independence number of the random subgraph is the same, the maximum independent sets also remain the same. That is, we don't get any new independent sets. Now, fortunately, in this one, the proof was exactly the same as in the case of permutations. That is, we were able to, define two kinds of things, a superstar and a force star, and basically consider the random variables counting each of them and use the exact same strategy. So far, we have seen 3 examples of random analogues for Erdős-Ko-Rado type results. Now, so what am I interested in doing next? So before going that, I'll just give a general framework. So in Erdős-Ko-Rado theorem, instead of just we can consider any family of subsets of an n set and ask what is the size and largest and structure of the largest families of intersecting sets in such a family G. So you take G, and inside G you consider families of intersecting sets. Now, one such thing would be a star, which is you take your favorite element X and consider all the sets in G that contain X. Now, such a thing is called a star. Now, the Erdős-Ko-Rado theorem, Erdős-Ko-Rado problem would be: what is the size of a maximum independent set bounded above by the size of a star? If this is satisfied, I'll say that this family G satisfies the EKR property. So if G, one can consider permutations as sort of subsets of some n by n set, and the set of permutations satisfies the EKR property. Now, the next question one could ask is, well, we have the size, size of any intersecting set in G is bounded above by the size of a star. Now, is this now the next thing we ask is, what is the structure? So is every maximum intersecting family necessarily a star? Now, the next question we can ask is, just as in the Hilton-Miller case, for Hilton-Miller theorem for the Erdős-Ko-Rado result, does every reasonably large intersecting family also lie in a star? So if we recall, in the beginning of this talk, I mentioned this Hilton-Miller theorem for the classical Erdős-Ko-Rado setting, where if you have an intersecting family of large enough size, then it has the same structure as that of a star. Now, this is one kind of stability result. Now, the other kind of stability result is, we could ask if a sparse random analog holds. That is, we transform this into a setting of graphs. So we can define a derangement graph. That is, you take the sets in G to be the vertices, and you join 2 of them if they're disjoint. Now, we could ask, we could form a model of random subgraphs of this and ask, so for what probabilities P does the independence number of the random subgraph be the same as that of the derangement graph? one could, pick, there are many generalizations of the Erdős-Ko-Rado theorem. So, pick one of them and one could try to solve this, attempt to answer this question of if a sparse random analog exists. Okay. So that's one thing I'm interested in doing. And so far, in all the three examples, the threshold probability at which superstars appear, that is, till certain probability P, if you go from 1, no superstars appear, and suddenly there's once we cross a threshold, superstars appear. And that is exactly the threshold at which the Erdős-Ko-Rado characterization fails. That is, till certain probability you have the Erdős-Ko-Rado characterization, and once you move towards the left, the Erdős-Ko-Rado characterization no longer holds. Is it necessarily that these two threshold probabilities are always the same? That is, can I get like some sort of a setup in which a superstar will appear much later than when the Erdős-Ko-Rado type characterization fails? So that is, it's kind of like a not such a well-formed question, but I'm interested in finding a setup in which the existence of superstars and then the failure of Erdős-Ko-Rado characterization happens at two different threshold probabilities. And with this, I'll end my talk. Thank you for your attention.
Thank you, Raghu, for the nice talk. Do we have a question for Raghu? Is there some specific family of graph? There was a Erdős-Ko-Rado problem you want, like the intersecting set has a connection to some nice graph, some graphs with nice structure, like permutations or derangement graph or your perfect matching graph.
Yeah, so so those are the ones we looked at because they're the most popular ones. And of course, one thing I interested in looking at is the vector spaces one. I mean, does the random analog hold for that?
Okay.
And of course, with the permutations, I just did it for all permutations, and there are many permutation groups for which we have Erdős-Ko-Rado. Like what, instead of taking the entire symmetric group, one could take a subgroup. For example, one could consider PGL to Q or something like that, and that's something that we also looked at.
Yeah. The vector space one is like a Grassmann graph or something. Like
Yeah,
that.
the Grassmann graph, yes.
Okay. Thank you. So in your characterization, there's the threshold. You need there's an epsilon inside.
Yeah.
What if P is equal to PC? It's not decidable?
Yeah, that's a good question. So that I think it takes a lot more. So so when I mean we haven't checked it, but when P is equal to PC, this particular probability could be say something like half or 2/3 or something. We haven't done that, but when P is PC, that's, as you said, that's something we're not entirely sure about. I think that might require like a different kind of tools and analysis.
Thank you. If there is no further questions, let's thank Raghu for the nice talk.